We previously talked about that the first law of thermodynamics says that in any process, whether it's a spontaneous process or a non-spontaneous process, the total energy of a system and its surroundings is constant. The system and the surroundings makes up the universe. So the first law of thermodynamics tells us that the energy of the universe is constant and unchanging. What the first law doesn't tell us is it doesn't tell us if a process is going to be spontaneous or if it's going to be non-spontaneous. The two factors that will determine spontaneity are the enthalpy or delta H and the entropy or delta S. Sometimes the enthalpy and the entropy will work together and sometimes they will oppose one another. This brings us to the second law of thermodynamics. This says in any spontaneous process, the total entropy of the universe must increase. So in a spontaneous process, we're increasing in disorder of the universe. The delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. If the delta S of the universe is greater than 0 or positive, that would mean that a reaction is going to be spontaneous. If the delta S of the universe is negative or less than 0, that tells us that a reaction is going to be non-spontaneous. We're going to go through a little bit of the derivations in the math that lead us to an equation we're going to talk about shortly. Don't worry too much about this. You won't have to derive these yourself. The entropy change for the surroundings will be equal to the heat transferred to the surroundings from the system divided by the temperature. So if we wanted to calculate delta S surroundings, we could take Q sub surroundings, which is heat of the surroundings, divided by the total temperature. The heat transferred to the surroundings will equal the negative of the heat added to the system. So that just says that the heat of the surroundings is opposite in sign of the heat lost by the system. So delta S surroundings can also be calculated by taking negative Q system, or heat of the system, divided by the total temperature. Changes of the system at constant pressure, or enthalpy we learned, is equal to Q sub P. So we can also take that negative Q system and sub in negative delta H subsystem divided by that same temperature if we wanted to calculate the entropy change of the surroundings. The entropy change of the universe can be written as delta S universe equals delta S system plus delta S surroundings. On the previous slide, we derived that delta H of the system over the temperature is also equivalent to the entropy of the surroundings, or delta S surroundings. We can rearrange this formula by multiplying everything by the temperature to get that out of the denominator, and that will give us the temperature times the delta S of the universe is equal to negative delta H of the system times T delta S of the system. And we said that for a spontaneous change, the delta S of the universe must be a positive value. So that means that the delta H of the system minus T delta S of system, that whole term there must be less than 0 if we're going to get a positive value for delta S of the universe, leading to a spontaneous process. The final formula that we derived brings us to something called Gibbs free energy, or G. This is the maximum energy in a change that is free or available to do useful work. It will actually tell us whether a reaction will be spontaneous or non-spontaneous based upon the sign. It'll allow us to determine the thermodynamic properties of the system, which is our reaction that we're interested in, and we won't have to consider the surroundings part anymore, or the universe part. Gibbs free energy, or G, is equal to H minus T delta S. Since it's an energy, it will have units of joules or kilojoules. We're usually interested in calculating the free energy change. Since all of these are state functions, we can say that delta G is equal to delta H minus T delta S, where our temperature is always positive and in units of Kelvin. We can also calculate delta G by taking G final minus G initial. G final would be like our products of our reaction, and G initial would be our reactants. We will learn a few different ways that you can calculate the Gibbs free energy change. In order for a reaction to be spontaneous, delta G must be less than 0. If delta G is negative, then we know the reaction is spontaneous as written. If delta G is positive, the reaction is non-spontaneous. And if delta G is equal to 0, the reaction would be in equilibrium. We'll look at that special case later. Spontaneous reactions will favor minimum enthalpy, meaning a negative value for delta H, and maximum entropy, meaning a positive value for delta S. Using the Gibbs free energy equation, delta G equals delta H minus T delta S, we can look at different conditions of delta H and delta S along with different temperatures to decide if a reaction should be spontaneous or non-spontaneous. For example, if we have a negative delta H and a positive delta S, that reaction is going to be spontaneous at all temperatures. No matter what you plug in for the temperature value, you will always end up with a negative value for delta G, signifying that it's spontaneous at all temperatures. If we have a negative value for delta S and a positive value for delta H, which would put us in the lower right-hand corner, no matter what you plug in for the temperature, your delta G will always be positive. So when we have the opposite signs for delta H and delta S than what would be favored, that reaction would be non-spontaneous at all temperatures. Nothing can overcome that and make the delta G be negative. It will always be positive. And then the two other ones are temperature dependent. If we have a negative delta H, but we end up with a negative delta S, now the delta H is the correct sign, but the delta S is the opposite of what it should be. Those reactions are going to be spontaneous at low temperatures when the delta TS term is essentially small and the negative delta H is what essentially drives that reaction to be spontaneous. If the temperature was to get too high, that T delta S term would overcome the negative delta H and create it being a non-spontaneous reaction. The last condition then is when we have a positive delta H and a positive delta S. In that case, the reaction will be spontaneous at high temperatures where the T delta S term is large and essentially overpowers the positive delta H term. So if the temperature was too low, that T delta S term could not overcome the positive delta H. So when one sign is opposite what it should be for a spontaneous reaction, the temperature comes into play. If both signs are the favored signs for delta H and delta S, a reaction will be spontaneous at all temperatures. If both signs are opposite, it will be non-spontaneous at all temperatures. Would you expect the following reactions to be spontaneous or non-spontaneous? In the first one, we have 2 moles of nitrogen plus 1 mole of oxygen, forming 2 moles of N2O. We have a total of 3 moles of gas on the reactant side, and we have 2 moles of gas on the product side. If we were to think about our change in our entropy, we went from more moles of gas to less moles of gas. This means that our entropy is going to be a negative sign because our reaction caused it to get more ordered. Our delta H for this reaction is a positive value. Delta H is positive 163 kilojoules, so this means that the reaction is endothermic. If we were to take these signs and plug them into our Gibbs free energy equation, delta G equals delta H minus T delta S, we could see what we would end up getting for our sign on Gibbs free energy change. Delta H is a positive value minus our temperature, which is always going to be a positive value since it's in Kelvin. There are no negative Kelvin units. And our delta S is a negative value. So in this case, we end up with a positive value minus a negative times a positive, which is another negative number. Notice that we now have a negative times a negatives, so we're going to end up having a positive number for our delta G no matter what. This is a situation where delta S is the opposite of what it would like to be, which is positive, and delta H is the opposite of what it would like to be, which is negative. So at all temperature values, delta G will end up being a positive value no matter what you plug in for the temperature, meaning that it's non-spontaneous at all temperature. In our second example, we have C3H8, which is a gas, plus 5 moles of O2, forming 3 moles of CO2 and 4 moles of gaseous water. There's a total of 6 moles of gas on the reactant side and a total of 7 moles of gas on the product side. We formed more gas, which means our reaction got more disorderly, so our sign for our entropy change would be a positive value, signifying an increase in disorder. Our delta H term has a negative sign out in front, so that tells us an exothermic reaction, and the reaction is producing heat. So in this situation, we have the favored sign for delta S and the favored sign for delta H. So right off the bat, that should tell us that our delta G for this reaction at all temperatures will always be negative. And that indicates a reaction that is spontaneous at all temperatures. If we want to plug in to the Gibbs free energy formula, we could plug in a negative sign for our delta H, and then it would be minus a positive sign for our temperature times another positive sign for our entropy. So in this situation, this reduces down to having a negative minus a positive. No matter what, when we take a negative value minus a positive value, that's going to lead us to having a more negative value. Hence why delta G will end up being negative at all temperatures. Let's try another example. Would you expect the following reaction to be spontaneous? We have 0 moles of gas on the left-hand side, and we formed 1 mole of oxygen gas on the product side. So our entropy change should be positive for this reaction since we formed some gas, which increased the disorder greatly. Our enthalpy change, or our delta H, is negative 98 kilojoules. So we have an exothermic reaction, and that's favored for spontaneous change. So according to the Gibbs free energy, delta G equals delta H minus T delta S. When we plug in our signs for delta H and delta S, no matter what, the algebra is going to work out that delta G will always be a negative value. So this reaction will be spontaneous at all temperatures. Will the following processes be spontaneous at high temperatures or at low temperatures? In the first one, we have a phase change of liquid water undergoing vaporization to gaseous water. We weren't given the delta H, but in this case, we have to understand that the enthalpy change for this process should be a positive value because your liquid water is going to have to absorb energy in an endothermic process in order to vaporize. Also, we are going from the liquid state to the gaseous state, so that tells us that our disorder is increasing in this process, so we should have a positive value for the delta S as well. If we use our formula for Gibbs free energy, delta G equals delta H minus T delta S, and we were to substitute in our signs, we're going to have a positive value for the enthalpy minus always a positive value for the temperature in Kelvin times a positive value for our delta S. In this case, we have a positive value minus another positive value. That could lead to a positive term, or that could lead to a negative term. We want a negative delta G if the reaction is going to be spontaneous. So we want this T times delta S term that to become very large. So when we subtract it from the delta H term, it ends up giving us a negative value. So this reaction would become spontaneous at high temperatures when that T delta S term is big. In our second example, we have silver ions plus chloride ions forming a solid silver chloride precipitate. The entropy change is going to be dependent upon ions in solution coming together to form an ordered solid precipitate. So we're going to have a delta S equal to a negative value because our reaction is causing it to get more ordered or less disordered by forming a solid. Delta H is negative, so it means this process is exothermic. When we look at our Gibbs free energy formula and we plug in our signs, we have a negative delta H minus a positive value for the temperature times a negative value for the delta S. This will reduce down to a negative minus another negative, which could end up being a positive or a negative value for the delta G. So this is a situation where we want to keep our T delta S term low so it doesn't overcome the negative delta H term. If we keep that low, we can end up getting a negative value for our delta G. So this would be an example where we have a reaction that is spontaneous at low temperatures only. We talked about the first law of thermodynamics, which discusses the energy changes of the universe being constant. No energy is gained or lost. We also talked about the second law of thermodynamics, which specifically told us if a reaction was going to be spontaneous or not, based upon the Gibbs free energy sign. And lastly, we'll learn about the third law of thermodynamics. The third law of thermodynamics talks about a perfect crystal having a minimum entropy at absolute zero. So the lowest entropy you can have, the lowest disorder, is when the temperature is at 0 Kelvin, which is defined as being absolute zero. At absolute zero, the entropy of a perfectly ordered pure crystalline substance is defined as being zero at that point. When it's at that coldest temperature of 0 Kelvin, essentially molecular motion stops and there's absolutely no disorder at that point. So we can say that the change in entropy is zero as well. We're going to use the concept of the third law of thermodynamics to talk about something called standard molar entropies. The numerical value that you see for the entropy of a substance can be determined experimentally, or it can be obtained from theoretical calculations. The standard molar entropies are measured with respect to an absolute reference point. That reference point is always the entropy of a perfectly ordered crystalline substance that is at 0 Kelvin, which is why it's defined as having a delta S of 0 at that point. The standard molar entropy, or S naught, is the entropy of 1 mole of a pure substance, specifically at 1 atmosphere of pressure and 25 degrees Celsius. The units are in joules per Kelvin times moles. Standard molar entropies you'll see of gases are typically greater than liquids, which are typically greater than solids. And the values will increase as the molecular complexity increases. So if you have a substance that has a lot more atoms and is bigger, it's going to have a greater standard molar entropy than something that is very simple. You can find a handout of standard molar entropies on Blackboard that contains many more substances than the short chart here that we're looking at. If you see S naught, that naught symbol refers to that atmospheric pressure of 1 atm and that temperature of 25 degrees Celsius. The units are in joules per Kelvin times moles. And you can see that the state of matter is always listed after the substance because that's important. If you look at, you have gaseous water and you have liquid water. They both have a different standard molar entropy. The gaseous water has a higher S naught than the liquid water because gaseous water has a greater amount of disorder than the liquid water will. So you also want to make sure that you're being extra careful when looking at the states of matter for different substances. The standard molar entropies you saw on the chart on the previous slide can be used to calculate the standard entropy of reaction. It can be calculated by subtracting the molar entropies of the sum of the reactants from the sum of the molar entropies of the products, multiplied by any coefficients from the balanced equation. Often, delta S subreaction with that naught symbol is just abbreviated as delta S naught. Remember, the naught just tells us that we have 1 atmosphere of pressure and 25 degrees Celsius that reaction was ran at. If we take the sum of the standard molar entropy of the products minus the sum of the standard molar entropy of the reactants, and use any coefficients from that balanced equation, we can actually calculate the numerical value for delta S. Our units will be in joules per Kelvin. Calculate delta S naught for the synthesis of ammonia. We have 1 mole of N2 plus 3 moles of H2 forming 2 moles of NH3. In order to calculate our delta S naught, we're going to take the sum of our products' standard molar entropies minus the sum of our reactant standard molar entropies. So we're going to have 2 times the standard molar entropy for gaseous ammonia minus, we're going to have 1 times the standard molar entropy of our nitrogen gas plus 3 times the standard molar entropy of our hydrogen gas. This is where the full chart comes in handy because now we can look up what these values are for the standard molar entropies of the ammonia, nitrogen, and hydrogen. So to calculate our delta S naught, we're going to have 2 moles times our S naught for NH3, which from our chart is 192.5 joules per moles times Kelvin. And you can see that your units of moles are going to cancel, and you'll be left with joules per Kelvin. That takes care of our products, minus we have 1 mole for our nitrogen times our value for N2 off of our chart, which is 191.5 joules per moles times Kelvin. Our moles will cancel again. And we want to add together our other reactant, which is our hydrogen. We have 3 moles times our standard molar entropy for hydrogen, which is 130.6 joules per moles times Kelvin. And that would be the sum of our reactants. Our moles is going to cancel. So here we have our products, just one, the ammonia. Here we have our reactants. So it's always final minus initial, with the final state being the products and the initial state being the reactants. This gives us an entropy change for our reaction of negative 198.3 joules per Kelvin. So we were interested in calculating that value. Now we could actually use that value to calculate delta G or do something else with it. We got a negative value for our entropy, and since it was negative, that means that the reaction became more ordered and less disordered. We also could have predicted that it should have been a negative value because we had 4 moles of gas on the reactant side, and we have 2 moles of gas on the product side. So just by looking at the reaction, we could have said, well, our delta S should be negative because we're getting more ordered by having less moles of gas on the product side. But we could not have figured out the 198 until we used those standard molar entropies. Let's try another example. Calculate delta S for the reaction. Solid calcium oxide plus 2 moles of HCl gas forming solid calcium chloride plus 1 mole of liquid water. To calculate our change in entropy for this reaction, we're going to take the sum of our products minus the sum of our reactants, multiplying by the moles from the balanced equation. So our products are the calcium chloride and the liquid water. We're going to have 1 times our standard molar entropy for calcium chloride plus 1 mole times our standard molar entropy for water, making sure that we're using the liquid value. That would be the sum of our products minus the sum of our reactants. We're going to have 1 mole times the standard molar entropy for our calcium oxide plus 2 times the standard molar entropy for our gaseous HCl. That would represent the sum of our reactants. So then we consult our chart of standard molar entropies for common substances, and we look up what those standard molar entropies are. Delta S for our reaction, we would have 1 mole times our value for calcium chloride, which is 114 joules per Kelvin times mole. Our moles end up canceling. Plus, we're going to have 1 mole times our standard molar entropy for liquid water, which is 69.96 joules per Kelvin times moles. Our moles end up canceling. Minus 1 mole times the standard molar entropy for the calcium oxide, which from our chart is 40 joules per Kelvin times moles, plus 2 moles times our standard molar entropy for HCl, which is 186.7 joules per Kelvin times mole. So our moles cancel, from the stoichiometry of the balanced equation. And that would represent the sum of our reactants. So coming up with a final value for our delta S naught, we get negative 229.4 joules per Kelvin. And once again, we got a negative value for our entropy that we calculated. So our reaction is getting more ordered, less disordered. We went from having 2 moles of gas on the reactant side to having 0 moles of gas on the product side. So once again, you could have expected that you should have a negative value for your delta S, whatever the number might be.